Okay, I hope you guys can see my screen.
Yes, please.
Okay. Okay. Good afternoon, everyone. So today is the week 5 discussion session for the course called Subsurface Exploration Importance and Techniques Involved. I am Balram Shah. I am doing my PhD at ICVA department at IIC Bangalore, and I am the PMRF TA for this course called Subsurface Exploration Importance and Techniques Involved. So I hope all of you have gone through the week 5 lectures. So we'll start the session. Okay, so I'll share the screen from this one. Wait. I hope you can see my screen. All of you can see, right?
Yes, sir.
Yes, yes.
Okay.
Yes, sir.
So what we'll be doing in this session will be seeing some sample questions for the week 5 lectures, and we'll be going through some topics out of that. Okay, so the first question is the discontinuity between crust and upper mantle. Okay, before that let me differentiate those. Okay, where is my pencil? Okay, this one. See, let's say we are dividing the earth, or we are taking one part or one portion of the earth out. Okay, so let's say this one is my portion that we have cut out from the earth's surface, or the whole earth. So this one is the crust, the upper portion. So now if we divide this crust, what we'll get, again, there will be, if we divide at very rough level, what will be those will be earth's crust, then mantle, and then core. Okay, so let's divide first like that. So this one is mantle, then we have core, correct? Now this mantle can also be divided into upper mantle and lower mantle. So let's divide like that. Now this one is the upper mantle, and this one is the lower mantle. And the core can also be divided into two, that is outer core and the inner core, right? Now now we can also divide this crust into, you, let us say there is some river, sea, or something, let us say sea. So this can also be divided into upper crust and lower crust, let us say. So this one is upper crust and this one is lower crust. Okay, now you can see the lines, right, between upper and lower crust there, and I have drawn one imaginary line. Then again, after the crust is over, the mantle is starting, there also I have started, or I have drawn one imaginary line. So these lines form the discontinuity, or from, let us say this is the crust and this is the mantle. So after the crust the mantle is starting, so the imaginary line that we are drawing between this crust and mantle is called discontinuity. Now every layers will have some discontinuities. First one is the discontinuity between the upper crust and the lower crust. You know what we say between this upper crust and lower crust, if we divide those continuity, that is called as Conrad discontinuity. Discontinuity. Similarly, if we see the discontinuity between the crust, or the, you can say, the lower crust or the upper mantle, then that continuity is called Moho discontinuity or Mohovicic discontinuity. Mohovicic, if the spelling is not correct, let me know. Mohovicic discontinuity. This Mohovicic discontinuity was named after the seismologist who have discovered or who have named this. And similarly, between the upper mantle and lower mantle, the discontinuity is called as upper mantle, and lower mantle it is called repeti or repeti. Spelling might be somewhat, it is not coming there. Repeti discontinuity. It's not coming. Yeah, it's coming. Okay. And similarly, this discontinuity between the lower mantle and the outer core is called as Gutenberg discontinuity. And the discontinuity between the outer core and inner core is called as Lehman discontinuity. Now, if we need to understand that what are the features of this crust, mantle, and core, then what we say, what we know about those. That crust, as we know, those are full of rocks or whatever we can see, right? And then if we move to the mantle, mantle will be having some rocks, then more semi molten state, then inner core will have the totally molten state, which will be like uh, rotating like that, and because of that electrical current type of thing will be generating, that will be coming later. Okay, but before that, let us understand the features that are there. Okay. Yeah. So density of most of the rocks on the earth surface is near to or less than 3 gram per cc and all. Okay, we will not go into deep of the features and all, but as we know that crust can also be divided into continental crust. Okay, so let me divide this as this. Okay, so this part, let us say, is the crust. This one you say as mantle, and this one as core. Okay, this one is crust, then mantle, and this one is core, total core. Now this crust can be divided into continental crust and the oceanic crust. So mainly the continental crust is composed of the granitic granitic rocks. Okay, okay. So mostly composed of granitic rocks, and the oceanic crust is composed of basaltic rocks. So mostly the rocks that are found in the crust are granites and basalt. Now if we come to the mantle, we know the mantle will cover the core part, right? And this mantle is composed of the 82% of the earth's volume is of this mantle. Now coming to the mantle, what kind of compounds are there? Mostly the compounds that are present in the mantle are the compounds are of silicates and oxygen, but other than this, mostly you'll get iron and magnesium also. Iron and magnesium in this layer. Coming to the core, uh, core is composed of mostly this 16% or nearly 16 16 to 18% of the earth's volume, and mostly it will be composed of iron and nickel. Now as we can see, mostly they see in the mantle and core part iron is there, so will be coming later that how the magnetic field will be coming in this. Okay, now why we are discussing all this, why we are discussing about the earth's crust, earth's core, mantle, why we are going, sorry, into this, because in the last lectures what we have seen, we were up to the indirect methods. And what were those indirect methods for having the subsurface exploration? Anyone? The
Seismic reflection, refraction, electrical resistivity, etc.
Yeah, seismic reflection, refraction. These three things: seismic reflection, seismic refraction, and the electrical resistivity survey. These we have gone through in the last session. Electrical resistivity survey we have gone through the last lectures. So today we'll be discussing about the magnetic survey or magnetic method. Then we'll be seeing the surface wave methods. Also we'll be seeing the gravity based method or gravity method if we say. And other than that there are some other methods like sounding profiling. Then magnetic anomaly test also we'll see. Magnetic anomaly test also we'll see today. Okay, so all of this we'll be covering today. Now coming to the magnetic survey, as we can see, as we have seen that how the earth is composed of, and we know that core will be moving or rotate, like moving like this. So what will happen because of this? What will happen? Some electric current will be generated. Is it? As we have seen in the mantle part and the core part, mostly iron is there. So as we are considering that the presence of iron is there at very high temperature, as we know, as we go deeper towards the earth, the temperature will be rising. So at high temperature in solid core, and as a result of convection current generated due to the temperature variation in the outer core, it will drive the inner core, and hence the this electric current kind of thing will be generated. Now we all know that if electric current is there, this means magnetic field will also be coming into the picture. Now as we all know that let us say we have one magnet having north and south pole. So what will happen? The magnetic field will be something like this. Is it? Something like this. Something like this. So now what we see, that if magnetic field is there, if magnetic field is there, okay, I have to write inside this. If magnetic field is there, there should be dipole, where because very much it is similar to the magnet. Only in the magnet we have the dipole that is north and south. But now coming to the earth, what we know, earth is also one kind of magnet. Why? Like we can consider earth as a magnet, can we?
Yes,
Yes, how?
we have north and south poles.
Yeah, because we have
Pole,
north
two
and
poles
south
we have.
poles. Yeah, as we
Yeah.
have north and south poles, we can consider this as a magnet. Right. Now coming to the polarity, let us say first, before that, let us say this one is Earth. Okay, before that, let us solve some questions. I was in the questions. We'll come to it soon. Okay, so the first question was the discontinuity between the crust and upper mantle is known as. Your options are Gutenberg discontinuity, Mohorvisic discontinuity, repeated discontinuity, Conrad discontinuity, and Lehmann discontinuity. Anyone?
Answer is B. B.
Mohorvisic discontinuity. So as we have seen just now, so the discontinuity between the crust and upper mantle is known as Mohorvisic discontinuity. So it's correct. Okay. Now moving to on to the next question. The discontinuity between the lower mantle and the upper core is known as. Anyone? Okay, so the question is what? the discontinuity between the lower mantle and the upper core. So just now what we have seen, bit from the lower mantle and outer core or upper core, what we see, what is the discontinuity name?
Gutenberg.
Gutenberg discontinuity. So the correct answer for this question will be Gutenberg discontinuity. Okay, so this discontinuity names you have to remember. Coming to the radius of the earth at the equator is dash kilometer approx larger than its, okay, this should come at the end, but okay, whatever. So as we know, where is my pen, that earth is not a spherical body, sorry, it's not, okay, I have no, but a elliptical body, kind of elliptical body, it's not exactly elliptical also. So now we can't say radius there, but if we say the semi major axis and the semi minor axis, because here what it has mentioned that the radius of the earth at equator and the radius at the pole. So as we know, for ellipse, it, this one is the semi, this one is the major axis and this one is the minor axis. I'm not going deep into that. So this length or this distance will be larger than this, isn't it? So let this be A and let this be B. So A is kind of total radius plus 21. Okay, so the radius of the earth at the equator is dash kilometer larger than its radius at the pole. What will be the answer? It will be 21 kilometer. Okay, it's clear why it is 21 kilometer larger at the equator, because it's not kind of spherical, it's kind of elliptical. It's not exactly elliptical also, but let us consider that it is an elliptical body, and it will have a semi major axis and semi minor axis. Now the radius at the equator means the semi major axis and the radius at the pole means the semi minor axis. Now the question is, how much semi major axis is larger than the semi minor axis? The question will, answer will be 21 kilometer. Okay, okay, so next one is the how do scientists or geologists understand the earth's internal configuration? Your options are based on analyzing the seismic waves during seismic events, based on the borehole data, based on the magnetic anomaly of the earth, all of the above and none of the above. Everyone, you can speak or you can write in the chat box. Simple answer is there.
Based on all these,
All of
magnetic
them.
also seismic. Yeah.
Okay, anyone else? You can write in the chat box the options if you want, or else I will move. Okay, so the all of the above will not be there, because based on the borehole data we can't go for the earth's internal structure or in earth's internal configuration. Why? Because uh, the borehole data will be limited up to a certain depth. We can't do borehole, or can't do drilling or boring up to the earth's core. So based on the borehole data we can't figure out what is the internal configuration of the earth. So the second one is gone. Based on the magnetic anomaly of the earth also, we can't, it is also limited to a certain depth. That will, this magnetic anomaly, when I will be discussing, then I will be explaining why not magnetic anomaly of the earth, because it is also limited up to a certain extent or certain depth. So the correct answer will be the based on the analyzing the seismic waves during the seismic events. Okay, clear?
Yes, please.
Okay. Now coming to the seismic waves, last day we have seen the seismic waves. Okay, so before seismic waves, let me go through what we were discussing that time. Where were we? Okay, so we were talking about the Earth's, what was that? What I was talking about? Magnetic field. Okay, so as we know, the Earth is having one magnetic north pole and magnetic south pole. Okay, and again, if let us consider this is a circle, the true north and the true south of the earth will be different, and this will be at an angle of 11 to 11.5 degree. Okay, this one is the true north, this one is the magnetic north, this one is the magnetic south, and this one is the true south. Okay, so there is one inclination of the axis present that will join the poles at about 11 to 11.5 degree with respect to the true truth, or the this axis that you can see where I have plotted true north and true south, that is called as the true axis, and this one is called as the magnetic axis. So there is magnetic north, magnetic south, and the angle between those will be around 11 to 11.5 degrees Celsius. Again, sorry, not degrees Celsius, 11 to 11.5 degree. Now this will also change during large period of time because of the wobbling will be there, then tilting will be there on earth. So this angle keeps changing, but on a very large period of time. Let's not go there. Okay, now coming to the change in polarity. What is polarity? We have two poles, north and south, so the property of having that is called as polarity. Now this now let us say in the top direction we are having magnetic north, and below we have uh, below we have magnetic south. Now this present configuration, let us say this one is the present configuration of magnetic north and magnetic south. This will keep changing over a large period of time. Now the period in which such change will occur is called as crons. Crons. What is crons? Period in which change of magnetic poles occurs. Okay, now coming to the normal polarity, what did I say? That let us say we have some pole configuration in the figure that you can see. Now at the top the magnetic north is there and magnetic south is there. Let us name it as something like A, B, something. Okay, that point I am naming as A and point as B. Now the pole configuration, now you can see A is at the top, B is at the bottom. Okay, so this one is called as the normal polarity. Whichever we are considering for the present configuration, that will be considered as the normal polarity. So normal polarity indicates the pole configuration matching with the present north and present south. Okay, so normal polarity is what? Normal polarity is referred with the present north and south. Now there is one thing called reverse polarity. So what did I say? That these poles will be changing over a period of time. Now when this true north, or sorry, not true north, the north that we are considering in the normal polarity, the north that we are considering in the normal polarity is reversed or is changed to the south. Sorry. Okay, what I was saying, reverse polarity. So let us say a situation, as I said, that the north and the south is keeps changing. Now it is changing, and at some point what happens, the north or the point A came just below at the point of B, and B went to A. So what happens, the whole polarity, the north became the south and the south became the north. But as we can see, it is north and south only, but only the polarity that was there at present has changed to the reverse. Okay, so now the reverse polarity will indicate a situation in which the present north will become the south pole and the present south will become the north pole. So this one was the reverse polarity. So in case of earth, it is called as geomagnetic reversal. Reverse polarity is clear. What is reverse polarity?
Yes, please.
Okay. So if this complete reversal is taking place, then that is called as last champ event. That is called as last jump event. Now coming to the as I said that the plate boundaries over the mantle or wherever it is, it will be moving. So what will happen, there will be a divergent boundary, and how this normal polarity will change to reverse polarity, and the materials that will be present at normal polarity at some period of time, it will at the reverse polarity, what will happen, that we'll understand first. So let us say two plates are there. Okay, this is one plate, let us say this is one plate. So both will be moving, let us say both are moving in the opposite direction. Now the materials that are there in the lower mantle portion, what will happen, that will come like this and it will get deposited here. So let us say at this time, let us say at t naught, what will happen, the materials will get deposited here. Now as what we said, that the polarity is changing with time. So after some time, the materials that is deposited at some point, it is shifting. So what will happen after some time, that let us say it is shifted to this side and this one, so and this one is shifted to this side. So the function the polarity when it was at t0, t0 is the present time when the present south pole and north pole is at the north and south, as we have pointed out. Then the materials that we can see was at the normal polarity, but after some time when the reverse polarity happened, then the material has shifted to some other location. So this one is the material at reverse polarity. Okay, so there will be some case like there is some normal polarity material, then again reverse polarity, again normal polarity, some normal polarity material is there. So some kind of layer will be created for a long period of time. So there because of those there will be a one we can calculate the average magnetic property of the medium. Okay, now coming to the magnet anomaly that we have seen in the that question, that what is, first of all, what is anomaly, what is anomaly, what is anomaly, anyone?
When polarity is seen to be away from normal,
Mm-hmm.
we find it to be different. We may call it to be a case of anomaly.
That is magnetic anomaly. Let us say only the
Yeah,
word anomaly, what we understand from the
anomaly
word.
is not normal, unusual, something unusual.
Yeah, something which is not whatever we have seen as the normal. Maybe that is not the normal, but let us say that whatever we have seen is the normal, and again after some years or some period of time we are seeing that some changes is happening. Now the changes that we can see from the normal that we are considering is called as anomaly. Now again if we see, let us say some precipitation, if we say precipitation, you understand, right? Now let us say that for 10 years one average precipitation we have for India, let us say 1200 millimeter. In the next year what we are seeing, that we are having 2000 millimeter of precipitation, let us say. So what we are seeing the there is one anomaly. Now how much is the anomaly? Anomaly is around 800. Let us say the average precipitation for the 10 years was 1200 millimeter, and the in the next year we got 2000 millimeter precipitation. So now what we are seeing is the anomaly from the mean or the average of 10 years. So this will call as mean anomaly or the average anomaly. Okay, so anomaly you all got right. Now coming to the magnetic anomaly, as Mr. Satish said, that let us say depending on the characteristic of the divergent plate boundary that we can see, the mineral deposited in the region should be indicative of the average magnetic properties, and that we are considering as constant throughout. Okay, so what will happen in case of some small magnetic, when it is coming in contact with the earth's magnetic field, it will exert some additional force. So uh, let us say there is some kind of other materials or some other deposits, some buried objects here, some we have buried some objects. So what will happen if we see the graph? What will happen? Let us say, okay, I'll change the color. The magnetic force is going something like this, and where it is coming to the buried object, it will go like this, and then again it will come like this. Okay, so because of the buried object, some ore deposits or some unconformity or something different is happening, then we'll get some anomaly in that. Okay, so such a change, if detected based on the field measurement, is called as magnetic anomaly. Okay, so why do we do this magnetic method, or why do we go for this field survey based on the magnetic method? Because we need to understand that how the subsurface medium is based on the observed magnetic anomaly, like based on the observed magnetic anomaly, what is the subsurface medium that is present in that. Okay, okay, let's move on to some questions first. Where is that PPT? Okay, seismic waves, I hope you guys remember, but still I will go through once because I need to have those. So there were four kind of seismic waves or shock waves. First one was the P wave, and the second one was the S wave. These two are what type of waves? We have learned in the last class. What type of waves are P waves and S waves?
Body waves.
Body waves, correct. And the other two are the Rayleigh waves and the love waves. See, as you can see in the P wave, only one kind of compression is happening. So particle motion is in this direction, the direction of propagation is seen. Now you can see every objects or every points, if you see, there will be compression and dilation into that. Now coming to the S wave again, in S wave you see the direction of propagation is the same, but what is happening to the body, only the body is getting curved in that direction, or shear is happening on that body. So that's why those are coming in bodies. But again, you if you see in the Rayleigh wave, what is happening, see similar kind of shock waves are there, but in S wave, all the particles, if you see, it is having that rectangular box all throughout. But if we see in the Rayleigh waves, all the particles or all the these points, if we consider, there will be some kind of motion or elliptical motion will be there, because of which the body's rectangular thing is changing at every point. Okay, so in the Rayleigh wave, elliptical type of particle motion will be there, and in love waves, as we can see, it is in the particle motion is in this direction. Now why we are discussing again this, that will come. So the question is, Rayleigh waves generates particle motion that are dash in nature. This is easy. That what will be the answer?
Elliptical.
Elliptical, correct. So the answer will be elliptical in nature. Next question is, which of the following statement is not correct? So the question are, sorry, the statements are: magnetic survey is suitable for the detection of geological faults. Then magnetic survey is suitable for detection of archaeological remaining in urban areas. With depth, the resolution of magnetic survey decreases. Magnetic survey is a quick method of exploration. None of the above, which is not correct.
This archaeological thing does not appear to be relevant.
But let us say, as we have seen in this here, what was the statement you said? Magnetic survey is suitable for the detection of archaeological remaining or something. Let us say we have, oh sorry, we have some, in the case of buried object, we have some archaeological remaining here. If some archaeological remaining is there, then don't you think that this curve, with that we can see that okay, there is some buried object or some archaeological remaining present in there, so that's why the response that we can see is changing, can't we?
Possible. Yes, yes.
Possible, na? Okay, let's see some other options. What are those? uh, faults or deposits, obviously it is suitable for that. With depth, the resolution of magnetic survey decrease. Obviously, if we go by depth, magnetic survey will be up to limit only, so that will also decrease. Magnetic survey is a quick method of exploration. It is a quick method of exploration. But as you said, the option B is correct only. But why it is correct? Why I went through that? Because if you see here, it is said as in urban areas. Now, in urban areas, we can't go for magnetic survey first of all, because we need a large area for magnetic survey. Okay, so even if we have archaeological remaining in urban areas, we can't go for the magnetic survey. Clear? Because of this urban areas, it will not come into picture. So the correct option will be B. Next is the period in which the change in configuration of magnetic poles takes place is defined as Kron's, last champ, geodynamo, or none of the above. In which the configuration of magnetic poles take place is called as, anyone? Srinath?
Crohn's.
Kron's. Okay. Okay. So the correct answer will be Kron's, as we have discussed earlier. So the correct answer will be Kron's. Next question is, in the surface wave method of exploration, which wave? Okay, surface wave we have not covered. So first let us complete this magnetic thing. So to do this magnetic survey and all, the instruments that we use. Sorry, the instruments or the instrument that we use is called as magnetometer. Magnetometer. And remember, this magnetometer is used to calculate the absolute magnetic absolute magnetic measurement, because we'll be coming into relative gravity also. That's why I have mentioned that magnetometer always measures the absolute magnetic measurement. Okay, so on this magnetic survey we can do by this on ground also, in air, satellite data also we can get for this. Mostly it is applicable for offshore structures and all. Before going to the subsurface exploration of offshore structures, let us say we are going to build some offshore structures. Before that, we do this magnetic survey kind of thing near the offshore. And where is this magnetic survey applicable? Mostly, as one I said, it is for offshore structures. Then other than that,
Rural areas.
mm, rural areas for.
Uh, for checking this polarity, etc.
Okay, anything other than that? So let us say we have some buried objects, as I said. Let us say some pipes or some drainage system and all. That also we can locate. Then we can map the landfills and all. Okay, so these small applications or offshore, as I said, is one of the important application of this magnetic survey method. So what are the advantages of this test? So in the question only, in that question, what was that question? We have seen. What is that question? Hmm. So here only we have seen it is a quick method of exploration. Then it is easy to do if we have the skilled laborers or skilled people. Then let us say for small vessel also in the offshore environment we can do this. But what are the disadvantages of this? Why we can't do it in urban areas?
There will be error, disturbance due to uh, magnetic materials.
Magnetic materials in urban areas. I didn't get how.
Urban areas, maybe transmission lines, etc.
Yeah, so that is electric current. Okay, so because of that,
Steam
magnetic
pipes,
field will be there. Correct.
eddy
Uh,
currents, and all.
yeah, correct. So let us say we have some scrap metal, we have some electric cables or the poles and all we have, that will alter or that will change the field observation, and that's why it is not suitable for urban areas, and that's why the option B will be the correct option. Now let us say material which is having the material magnetic characteristics, if it is present in the uh, nearby areas, then it will also be detected in the form of anomaly. So that also, there also we can't do this. And as we have seen here, the option C, with depth the resolution of the magnetic survey will decrease. Okay, so magnetic survey and magnetic anomaly test and all we have seen. Where was I? Okay, now coming to the surface wave. Surface wave, what we have seen, that what all surface waves were there. First of all, the shock waves or seismic waves we have seen. What kind of shock waves we have seen? We have seen the body waves, those are P waves and S waves. And we know why S waves is important, because S wave, as we know, is also called shear wave. Okay, this all I have discussed in the last class, but I need that. So shear wave, why do we need to think about shear wave? Because with the shear wave we can calculate the, or we can obtain the shear strength of the medium or the soil, that whatever is there. And from let us say several seismic scenarios are there, this much seismic event with this much intensity or this much magnitude, some different seismic event you are, or seismic scenario you are considering. In that case, for different seismic scenario, what is the shear strength of the medium or the subsurface mediums that are there? For that we need the shear wave. So to identify the medium in case of different seismic scenarios, the shear strength of the different mediums we can understand. So there we need this S waves. Again, what all we know, that there are surface waves, as we have seen. Surface waves are Rayleigh waves and love waves, isn't it? So as we have seen, Rayleigh waves are having the particle motion in elliptical motion, kind of ripples in water, and the love waves are translational in nature. But now coming to the surface wave test. In the seismic reflection survey and seismic refraction survey, what we have seen, how it is going by body. But now coming to the surface waves, why we are not using the P waves and S waves also? Because first of all, it is body waves, but mm, not that case. Let us say near the surface of the near the ground surface, if you see the body waves, then in those case what will be there, the signal to noise ratio, let us say signal to noise ratio, or we can say S by N ratio, will be low near the ground surface. Okay, so why the signal to noise ratio near the ground surface will be low?
Because of disturbance.
Yeah, because there are from the surroundings there will be several other sources that are generating waves. Okay, let us say we have the we have the source which is giving the shock wave. But if we consider the ground surface, there will be several other shocks that will be there from the surroundings, or the waves that will be generating from the surroundings, and that will be considered as noise, because we are going, whatever observations that we will take, we'll considering that the waves that are generated is from the source. But if we have some source or some waves that is coming from the surroundings, that will interfere in our calculations, so that will be considered as noise. Hence at the ground surface the signal to noise ratio will be low. Okay, so this is one of the reason why we are not going for body waves like P waves, S waves and all. So which wave we'll consider? We'll consider the Rayleigh waves. So we'll consider the Rayleigh waves. And one of the main advantage, or one of the main good thing, or you can say for the Rayleigh waves, that it is having low frequency and low velocity, but it is having high amplitude. So high amplitude means what? It will have high signal to noise ratio. Okay, so that's why we'll consider this Rayleigh waves. Now if we know the shear wave velocity, from that also we can calculate the Rayleigh wave velocity, but at low strain. Let us say at low strain we can calculate the Rayleigh velocity. This one is the Rayleigh wave velocity. Rayleigh wave velocity. Okay, I should not write like this. Vs is the shear wave velocity. Shear wave velocity. Then at low strain, Vr is given as 0.9194 Vs. These small formulas you have to remember, because these small formulas you can't, maybe they will not give in the exam. So these small formulas you should remember. The bigger formulas you can skip, I guess. Okay, so what I was discussing. Okay, so use at low strain we can calculate the Rayleigh wave velocity if we have the shear wave velocity, and if we plot this velocity versus, we have seen in the last class that for different Poisson's ratio the velocity will be changing. So let us say wave velocity is on the y-axis and Poisson's ratio is on the x-axis. So from the formula only we can see that if, let us say, the shear velocity is something like this one is the shear velocity profile, then what will be the Rayleigh wave profile? Whether it will be upward or lower, or how, what kind of profile will it be?
Lower.
Lower, because see, Rayleigh wave velocity is 0.9194 or 91.94% of Vs, so it will be somewhat like this. Okay, I will use some other color. So sorry. So this one will be my Rayleigh wave velocity. And coming to the P wave velocity, what will happen? In P wave velocity, as we know, it is much higher than the Vs. So P wave velocity will be something like this. Okay, this will be P wave velocity. Now based on the P wave velocity, or based on the Vs, as we have seen, based on the P wave velocity and all, we can also configure what is the density, and then we can go for what is the subsurface medium. Similarly, this Vr can be used to estimate Vs, then Vs we have used to classify the subsurface medium. Okay, let us say if Vs is somewhat, there is some value, right, 180 meter per second, then it is soft medium. If it is greater than 150 and between that, then it is weathered rock or very stiff soil, let us say. So based on the this shear wave velocity, we can understand what kind of medium is present in the subsurface. Okay, now moving on to the questions. Okay, in the surface wave method of exploration, which wave is used to estimate the shear wave velocity? Which wave is used? This is simple. In the surface wave method we are going through, as we have discussed, to estimate the shear wave velocity, which wave we need to have? Just now I have
Rayleigh.
Rayleigh wave. See, if we have Rayleigh wave, then using the Rayleigh wave we can estimate the shear wave velocity, and if we have shear wave velocity we can easily get what type of subsurface medium is there. Okay, so where is that? Okay, so which wave velocity is used? So answer will be Rayleigh wave. Next one is, at low strain Rayleigh wave velocity is equal to shear wave velocity, less than shear wave velocity, greater than shear wave velocity, or none of the above. Just now we have seen, we have plotted one graph also from
Less.
velocity and
Less.
Poisson's
Less.
ratio, and we have seen the formula also. So tell me, which one will be the answer?
B.
Yeah, correct. Less than shear wave velocity, because Rayleigh wave is 0.9194, and if we have seen here also, this one is the Vs and this one is the Vr, isn't it? I hope everyone is getting. Okay, Gopal also gave the answer. S wave. Did you say the last answer? Oh, uh, everyone is getting, right? Everyone is with me. If you are having any doubt or something, you can just stop me there, you can ask me. Okay, it's not something like a class, as I said in the first class only, that it should be one interactive class. It should not be like you are having lectures. If you are having any doubt, I am here to solve your doubt. Okay, no question is small question or something. All are with me?
Yes, sir.
Okay, okay, okay. So I will move then. Okay, wait. Okay, sorry, I have not. This one will not be A. Sorry. This one will be B only. Okay, so this one will be B. Correct. Now the question is, the higher frequency content of a signal received in a geophone receiver is dominated by geophone and all we have seen last day, geophone receiver. So the question is, the higher frequency content of a signal received in a geophone receiver is dominated by which waves? Waves coming from the shallower depth, waves coming from the deeper depths, waves coming from the interface of two layers, or none of the above? This is an interesting question. We are having the high frequency content of a signal received in the geophone.
Uh, High frequency means low amplitude.
Hmm.
So maybe from a shallower depth.
Okay. Correct. So as we are having higher frequency, so higher frequency means what? That the waves will be coming very fast, right? Frequency is what? Frequency is like in one time period, let us say how many waves that you have got. So higher frequency means high number of like high number of waves or period, you can say oscillations, you can say, that you have got. So higher frequency means low amplitude signals. Low amplitude signals means the P waves, S waves and all, or the direct waves that we are getting, that will be dominated in the geophones. Okay, in the last lectures also we have seen. So the answer for this will be the waves that are coming from the shallower depth, because from the deeper depth, as we have seen, what kind of velocity will be there, the Rayleigh wave velocity and all. And as we have seen, the Rayleigh wave velocity is a low frequency signal with high amplitude. So the geophone receiver, if it is dominated by the higher frequency content of a signal, then it will be the waves that are coming from the shallower depths. So the correct answer will be A. Moving on to the next question, which of the following statement is correct? The ratio of shear wave velocity to Rayleigh wave velocity is always less than 1 for a fixed depth and wavelength. The amplitude of the vertical component of Rayleigh wave increases with increase in Poisson's ratio. For a fixed depth and wavelength, the amplitude of the vertical component of Rayleigh wave increases with increase in Poisson's ratio. The amplitude of displacement of the Rayleigh wave at a certain depth can never be more than the amplitude of displacement of the Rayleigh wave at the surface. None of the above, both A and B. Okay, read it carefully because it's saying kind of large statements, and then tell me the answer.
D appears to be the answer.
None of them is correct, is it? The ratio of shear wave velocity to the Rayleigh wave velocity is always less than 1. Velocity. So Vs by Vr is always greater than 1. Okay, so first one is not correct. Okay, then for a fixed depth and wavelength, the amplitude of the vertical component, of the Rayleigh waves increases with the increase in Poisson's ratio. But second one is the correct only, na? For a fixed depth and wavelength, the amplitude of of Rayleigh wave, vertical component of the Rayleigh wave, okay, increases with increasing. Second one is correct only. What is the third one? Let's see. Uh, the amplitude of displacement of Rayleigh wave at a certain depth can never be more than the amplitude of the displacement Rayleigh wave at the surface. No, this is not correct. The displacement of Rayleigh wave at a certain depth can never be more than what? Okay, what is they are saying, that amplitude of displacement of the Rayleigh wave at a certain depth, let us say d, can never be more than, this means less than the amplitude of the displacement at the surface. This is not possible. This is not correct. Okay. So second one seems to be correct. Why you are saying that none of the above? Why the second one is not correct? Anyone else wants to give the answer? Anyone else? You can write in chat box also if you want. Which one is the correct answer? What a fixed depth and wavelength. B. Anyone else? Srinath, Mr. Devi Prasad. Sorry, sorry. Okay, see, what they are saying is, for a fixed depth and fixed wavelength, okay, the depth is fixed and wavelength is fixed. Now the amplitude of the vertical component of Rayleigh wave will increase with the increase in Poisson's ratio. The Poisson's ratio is increasing. Okay. Now if the Poisson's ratio is increasing from depth is fixed, the amplitude is also fixed. Okay. Now if the depth is fixed and the wavelength is also fixed, only the vertical component, if you see, of the Rayleigh waves, the wave is traveling like this, there will be an elliptical motion like this. Only the vertical component, if you see, then what will happen? It will increase with increase in Poisson's ratio. If the Poisson's ratio is increasing, obviously the Rayleigh waves vertical component will increase, the amplitude of that. Okay.
Right, right.
Okay, so the correct answer will be B. Okay. Next question is, which of the following is or are correct for multi-channel analysis of surface waves? Okay, so before moving on to this, there was one dispersion of wave. What is dispersion of wave? Just to complete what all we are doing, because I should go in one layer. So what was dispersion of waves? What is dispersion of waves, or what is dispersive medium? If I ask, what is dispersive medium? Let's say two mediums are there. Okay, this is the soil layer 1 and this is the soil layer 2. Okay, now the waves are passing. Now if the waves are passing, all the frequencies are traveling at same velocity, let us say, then what we say, that that medium is non-dispersive, because what is happening, the amplitude, the frequency that is the waves are coming with some amplitude, with a specific frequency. Now what will happen if the medium is, let us say, heterogeneous? Okay, so what will happen, the waves that are traveling, it will disperse. Okay, now because of this the velocity will be reducing, because the waves frequency and amplitude are changing. Now the velocity will also change. So if the all the frequencies of the wave are traveling at the same velocity in medium, then that medium is called as non-dispersive medium. Okay, did you get what is non-dispersive medium? So the opposite of that will be dispersive medium, that if the frequency content or the let us say Fourier spectra of at source and the receiver is getting dispersed, then the difference frequency of the waves will be traveling at different velocities. Now if the different frequencies of waves is traveling at different velocities, that medium, or in the medium in which it is happening, is called as dispersive medium. Okay, so mostly this dispersion will occur in heterogeneous medium. Okay. Now let us say we have lower frequency content. So if we have lower frequency content, then what kind of wave it will be? Larger or shorter? It will be larger wave, isn't it? Okay. So if the layer is having very stiff soil, then what will happen? The velocity of the Rayleigh wave will, as we have discussed in the last class also, the waves I am going fast because we have discussed in the last class. If the material is stiff in the medium, then velocity will increase. Correct. Oh, well, it's correct. So if we draw the graph, or we can say one dispersion curve is there, then that dispersion curve looks like what? It is the plot between the frequency content of the medium, or the waves frequency content, and the phase velocity. Okay, so if it is at a deeper depth, okay, then velocity will be what? If it is deeper depth dominated, then phase velocity will be increasing or higher. And as the frequency is increasing, so what will happen, the shallower depth will be dominated. So here it will be deeper depth dominated, deeper depth dominated, and at this point it will be shallower or shallow depth dominated. Okay, so from this dispersion curve, what we can understand, we can understand the characteristics of medium, the heterogeneity of the mediums, heterogeneity. Okay, dispersion curve is clear. What is dispersive medium, what is non-dispersive medium, and why it is happening and all. Did you get those, everyone? So in the lecture you have seen one plot between the amplitude at, let us say, at what is the ratio between the amplitude at depth to the amplitude at the surface, with the depth and the wavelength that will be changing like this. Okay, from there you can know the amplitude of wave, it is decreasing, then what kind of Poisson's ratio it will be. Okay, so from there only we can understand what will be the Poisson's ratio, whether it is increasing or whether it is decreasing for the particular wavelength and depth. Okay, so the correct the question that we have, the option B, there was one plot like this, I don't remember it properly. It was the amplitude, okay, amplitude at some depth, let us say, divided by the amplitude at the surface. It was the plot between this and the depth by wavelength. Okay, and if we are going like this, it was till 1 or something, so it will be traveling something like this. For different Poisson's ratio there will be different these type of curves, if you remember exactly. Okay, now sorry, the curve was something like this for different points Poisson's ratio. For different Poisson's ratio, um, different Poisson's ratio, the curve will be changing. Okay, it was some negative here, or it will start from 0 here, and as it will go this side it will be negative, and this side it will be positive. Okay, so from here we can answer that question. Now coming to the surface waves, what all surface waves we have seen? The MASW and the SASW. In the last class also we have. MASW is what is the full form of MASW? Anyone?
Multi-channel analysis.
Multi-channel analysis
Surface waves.
of surface wave, correct. So it is multi-channel analysis of surface waves, correct. And SASW is spectra analysis of spectra analysis of surface waves. Okay, don't miss it with shear waves, it is surface waves. Okay, so based on the dispersive characteristics, this MASW and the SASW is taken care of. Let us say the dispersive characteristics over the multiple frequencies, or the, let us say, multiple channels, using number of we have number of geophones, and then we are getting the dispersive characteristics. So fundamental based dispersion curve from the field record that we have seen here, that dispersion curve that we have seen, if it is at higher modes, we have higher let us say fundamental mode based dispersion curve is there from the field record, and dispersion curve is there at higher modes. Then from that we can understand, okay, for there are several number of geophones, and from that we are getting the dispersion curve. Then we'll say that multi-channel analysis of surface waves we are doing. And in spectra analysis, what we do, we consider one pair of geophones only, and then we move it, and then we get the observations. Okay, so that is called as spectra analysis of surface waves. Now in this surface waves we have completed. Now coming to questions, let us see some questions. So which of the following is or are correct for multi-channel analysis of surface waves? Your options are: multiple geophones are used in this test, shear wave velocity at different layers can be found using MASW, the depths of the soil layers are calculated based on the arrival time of the direct, reflected and the refracted waves. Both A and B, all of the above. Read it, then let me know. E, okay. So all of the above you are saying. Okay. Anyone else?
Uh, Using surface waves, I think we can't get these reflected and refracted waves.
Hmm. Because in seismic reflection and refraction survey, we get the reflected and refracted waves. That will not be the correct option. So what will be the correct option?
D.
D, both A and B. Okay. First one is correct, because as just now I said that multiple geophones are used in this test, and in the SASW test, what we do, we consider one pair of geophones, only two geophones, and then we move that, and then we get the. Then next question, next option is shear wave velocity at different layers can be found using. So anyway we are doing for this for MASSW, we will get the this Rayleigh waves velocity, and from there we can calculate the shear wave velocity, as we know. So this one is also correct. So correct answer will be both A and B, because reflected wave, refracted waves, direct waves, this will get from the seismic reflection survey, seismic refraction survey and all. Okay, so the correct answer will be D. Okay, moving on to the next question. Okay, gravity. So before that I have to explain somewhat. Okay, so this one is the last part. So in the seismic survey, what we have seen, how we are quantifying the subsurface medium. We are quantifying the subsurface medium based on the shock waves that we are producing. Based on the shock waves, how much resistance it is creating. Based on that, we can understand, okay, these are the subsurface medium. Then we have seen the electrical resistivity survey method. In that, what we see, that we are putting two electrodes based on the electric current, or the electric current that is passing, the resistance or the apparent resistance that we have seen. Apparent resistance and true resistance I have explained in the last class. So based on the apparent resistance, we know the what is the, okay, sorry. Wait a minute, I think I lost the connection in this one. Shit. Hello, can you hear me?
Yes.
Okay, I lost the internet connection. I'm sorry for that. Wait, 1 minute. Okay. Okay, where was I? I was explaining the. Okay. So in electrical resistivity survey method, what we were seeing that based on the apparent resistance provided from the medium, we can understand what are the subsurface medium. Now coming to the gravity survey method. Sorry. Now coming to the gravity survey method. Anyway, we know that for subsurface exploration, why we are doing, to understand the, or to characterize or to identify the subsurface medium. Now in the gravity survey method, what we do, we based on the difference in the relative gravity at observation point, with the reference to its value, considering the some general conditions, based on the, okay, I will write, based on the difference in relative gravity between or at observation points, we do the gravity survey method, and from there we can characterize or identify that what kind of subsurface medium is there. Okay. Now every we all know that what is gravity and all, so I'm not going deep into that. But how this gravity is changing, gravity can change because of the subsurface medium, as it will lead to mass, because mass, as we know, this every object will contain some mass, and because of that we are having the force of attraction. Okay. And this mass is, the force of attraction is directly proportional to mass based on the Newton's second law of motion. So that is called as gravitational pull and all. I'm not going to those things. So this gravity or gravitational pull, how it will change, the gravitational pull will change based on the type of subsurface medium. Then what is the height of observation, or what is the altitude of the observation with respect to some datum, let us say from the mean sea level. Then where do you have, what is the latitude, based on the geographical location. Also the gravity will be changing, because as we know, at equator the gravity, whatever is there, at pole if you see, it will be changing, it will be different. Temperature will, let us say when we are recording, what is the temperature, then based on that also, the this what this gravity will be changing based on the shape, size, orientation. Based on all of this, the gravity will be changing. Okay. Now, so I'm not going how it is changing and all. So what we do while observation or all, what we do, we are taking some gravity. Okay, let us say that there is some layer of soil. Okay. Now what happens, we are having some let us say some rock pockets here. Okay, some rock pockets with higher density than the surrounding, higher density than the surrounding. Then what will happen? Then let us say we are seeing based on the distance what is the gravitational pull. And what we'll see, it is going like gravitational pull is going like this. When the rock pocket with the denser medium is coming, it will increase, and then again it will go like this. So this one is the gravitational pull line, gravitational pull. So what will happen? Because of the this rock pocket, there will be one gravity anomaly. Okay, and similarly, okay, similarly, let us say we have, I'm extending the layer. Let us say we have lighter medium. Then again, this is lighter medium. Then again, after some point, some denser medium is coming, but not in the horizontal fashion, but like this. So see, this one is what? This one is some kind of discontinuity or some kind of fault, let us say. So what will happen? Again, this gravitational pull will be coming like this, but again, where is this starting? Here, let us say. So what will happen here? It will come like this because of the discontinuity, because it is changing from the lighter medium to denser medium. So the gravitational pull will be increasing, and as after that, what is there? It is denser medium only. So it will go like this. Okay, got it? So now to calculate this gravity, what we use, the instruments that are most commonly used are stable gravity meter, gravimeter. Okay, stable gravimeter are simple, that a mass will be suspended from the vertical spring, and any extension or the, let us say we are pulling it, then what will happen? The spring will be the length of the spring will change, and based on the indication of the change and all, we'll calculate the gravity. Simple, in the pendulum also we can do the gravity like that. So after that we have Lacoste-Romberg gravimeter. When this was introduced, it was a very nice setup. So in this one hinged beam, okay, I'm not going deep into that. A hinged beam is there which will create, which will carry a mass which will be attached to a spring, and then we'll again extend this, and based on that we'll calculate the this gravity. But again, this one is more precise than that of the stable gravimeter. But what happens, we have to control the temperature, because it will only if the temperature is changing, what will happen? The hinged beam that is there, it will have some deformation. So because of that, this Lacoste-Romberg gravimeter, whatever is there, we need the temperature, like we have to require the temperature controlled environment. Okay, after this we have GCG5. Okay, like this we have some more gravimeters where we can calculate the what is the gravity. Okay, now anyway, we have seen what are the, like how the gravity is changing, because of what all, because of tides, because of pull from the, let us say, sun, some other celestial objects. Then based on the elevation, based on the geographical locations, based on the topography, based on glacial isostatic uh, adjustment, based on several factors, this gravity will be changing at some point. So after let us say we are getting the gravity value, after getting the gravity value we have to do some corrections. Okay, so the corrections to be applied to the field observations. So what are the corrections that are to be applied? Anything, anyone? Some simple corrections that need to be applied.
free air correction.
mm, free air correction. But before that, simple, let us say some instruments is there that like as we said in stable gravimeter, these all will get the gravity anomaly, or we can say the change in gravity. So after getting the gravity anomaly, we have to deduct all the mean value or the measurements that we have to get the proper gravity value, because all this will give you the gravity anomaly value. Okay, so we have to take the difference for the this gravity anomaly thing. Then we have to go for calibration of the instrument or the calibration. So for based on all the whatever instrument we are using, we have to like whoever is preparing, whoever is making that instrument, they will give one calibration chart or something. Based on that calibration chart, we'll do the calibration of the instrument. Then we'll have the drift correction. What is drift correction? What is drift correction? So correction is something like, let us say you are getting the observation from the morning to evening. Now what happens to, because the time has been changed from morning to evening, there will be either some deformation in the spring, let us say some creep or some elongation in the spring. So because of that, we have to do some corrections called drift correction. mm. So mainly this whatever gravity and all we are seeing, the correction we'll do in milligal. Okay. Milligal or milligalileo, whatever you say. And as we said, what all other factors we have seen, what all other corrections were altitude correction, because if you are altitude correction, correct. Let us say you are changing some, you are doing at some plane, then you are doing at some hill, at some mountain. What is happening, the altitude is changing. Now based on whatever datum you have considered, or based on whatever reference you have considered, there will be some altitude correction. Okay, so gravity value will change with the change in altitude, as we know, if the altitude is changing, the gravity value will be changing. Let us say if you are at a plain land and you went too far away the peak of the mountain, so where will be the gravity will be less, on the plane or the peak of the mountain? It's a simple question. Where the gravity will be less, at the plane or at the peak of the mountain? Peak of the mountain, correct. So as the altitude is increasing, the gravity will be decreasing. So with reference to the mean sea level, with increasing the altitude, the value of the gravity will be decreasing with the height. Okay, and this is also known as the free air correction. So this free air correction will be given as 0.3086 into height. H is the altitude or the height from the whatever mean sea level, or mean sea level mostly we consider as the datum. If you are changing the datum, so based on that datum only you will have to calculate all the altitudes. Based on that reference point, whatever you have calculated, or based on that datum whatever altitudes you have calculated, the height will be calculated in that, though. So the height will be in meter, and then you will get this del GFA or the free air corrections. Now let us say if the point wherever you are calculating the gravity, that is above the datum, then what will happen, the corrections that you are seeing will be positive. And let us say if this is the datum and you are calculating the gravity here, then what will happen, the corrections will be negative. So this can be both positive or negative based on where you are calculating the gravity. Next one is the latitude correction. Latitude correction or geographical location correction, gn will be given as ge into 1 plus beta 1 into sine square lambda plus beta 2 into sine square lambda. Okay, where Gn, as I said, is the latitude correction in milligal. Okay,
I
and
think second term, third term has the power of 4. B2 sine.
yeah, correct. Thank you. Yeah, correct. Okay, so what I was saying, Gn is the latitude correction, G is the gravity at equator, E for equator. Okay, gravity at equator. Okay, and beta 1 and beta 2 are coefficients that will be given, and these values will be depending on the like what is the speed of rotation of the earth. Okay, and what is left, lambda is the latitude at the observation point, observation point. Okay, so this type of latitude correction will be there. Then there is Boger slab correction. When do we do this Boger slab correction? What is Boger slab correction? Let us say, as we have seen, because of the convection current and all, the this materials from the mantle will be coming out and all. Let us say because of that, or let us say some glacier isostatic adjustment happened. Okay, so because of that, what will happen, either some mass or some mass of some layer has been removed from there. Okay, or let us say some excess mass has been coming to the observation point. So now the correction that will account for this excess mass that is existing between the observation point and the datum, that is called as Boger slab correction, because it is some kind of slab. If some excess kind of mass is there, it is kind of slab. That's why we are calling it as a Boger slab correction. Now this Boger slab correction will be given as 0.04193 rho into h. This small formula you you have to remember. This they might not give in the exam. Okay, so I am telling you from here only. So what I was saying, this rho is what? Rho is the mass density of the medium, mass density of the medium, or the excess mass, that you can say, excess mass. And h, as we know, is the height of observation point in meter. Okay, and other than this also we do several corrections such as terrain correction. As we have seen that if mountains and all are there, there will be uh, several change in the gravity, so we have to do the terrain corrections also. But let us say we are doing the, for regional studies, let us say it's full plain land, then we don't have to go for this terrain correction, because if it is plain land, it is a level terrain, so we don't have to do this correction. And then we have tidal correction. Other than these also there are several corrections based on how, what is your type of study, whether you are doing for regional study or you are going for very large, very large area, then based on that there are several corrections and all. Okay, so these are some kind of corrections that we do. So where do we apply this gravity survey method? Let us say we need to understand what are the fossil fuel or the mineral deposits. What mainly we are going for subsurface exploration, so mainly for the fossil fuel or the mineral deposit exploration. Let us say to understand the underground water and all this cavities and all, we are going for this gravity survey method. Now coming to the questions. Okay, so the question was, what is the absolute value of free air correction if the gravity is measured at an elevation of 70 meter above the datum? So they are wanting the free air correction. Free air correction means the altitude correction you want now. Sorry. So you have to calculate the free air correction when the height is given as how much? 70 meter above the datum, and the datum is given as mean sea level in this case. Okay, so calculate, let us see how much you are getting. Formula I will write for your reference. Del GFA equals to 0.3086. Del GFA equals 0.3086 into h. Simple, it is simple. How much I am getting, let me see. To 70 meter, how much you are getting? Okay, Srinath, option B. Gopal, option B. This. Anyone else? And mostly option B. Whether the options are correct, whether it will be positive or negative. Positive only, because they have said that it is at an elevation of 70 meter above the datum, and what I said, if it is above the datum it will be positive, if it is below the datum it will be negative. So if we put the value here, 0.3086 into 70, we are getting something like 21.602 milligal. So the correct answer will be B. Everyone got, I guess. Okay, so the correct answer will be B. Okay. Okay, so the next question is, what is the absolute value of free air correction if the gravity is measured at an elevation of 60 meter above the mean sea level? Oh, simple question. Same question, similar type of question, just value will be changing, I guess. How much? Just reply in the chat box or wherever you want. 3086 into 60. Okay, see, correct only. So
C.
if you calculate it, will get something like that. Okay, next one is, what is the Bogor plate correction to a medium having a mass density of 3.1 gram per cc at an elevation of 80 meter? Okay, I will give you the formula. Del GB is how much? What was the formula? 0.04193. 0. Oh, sorry. 0.04193 rho each. Rho is given as 3.1 gram per cc. H is given as 80 meter. Now simple, you have to put 04193 into 3.1 into 80. How much you are getting? Srinath, option B. Gopal, option B. Anyone else?
B.
B. Yeah, correct. So we are getting 30, something like this. Okay, next question. Oh, also similar only. Do it. Formula if you want, I can show. 0.04193 rho h. How much? 0.04193 into 2.60. C, C, C. Okay. Yeah, correct. It will be C. 6.037. Okay, it was same. Okay, I'll move to the next question then. Right? Okay, sorry. So the question is, what is the value of G, or the gravity, corrected for latitude correction during gravity survey for a location having coordinates of 50° east and 60° north? Consider beta 1 as this much, beta 2 as this much, and gravity at the equator, that is GE, as this much. What you need to find out, what is the value of G corrected for latitude correction. You have to do only the latitude correction. formula if you want I can give. Wait, what is the formula? G into 1 plus beta 1. Okay, it was GE into 1 plus beta 1 sine square lambda plus beta 2 sine to the power 4 lambda. Let me check once. Yeah, GN. GN. Do it. Srinath A. Okay. No one else? Wait, wait. Divya Prasad also A. Mr. Satish, did you get?
Uh, Lengthy calculations. I'm stuck up on this.
Okay. So let me see how much I'm getting. Gopal, did you get how much? So the correct option that I have given is okay D. So I have to do it. Okay, how much is the latitude? Beta 1 is given, beta 2 is given, G is given. How much is the latitude? Lambda is how much?
60.
Yeah, correct. So latitude is how much? 60 degree north. Okay. So just put it. G is how much? 978031.86 into 1 plus beta 1 sine square 60 plus beta 2 sine to the power 4 60. Okay, let me do it. Where's my calculator, man? Sine 60 into 0.0052788895 plus 1 plus 0.00002346 into sine to the power 0 60. Shit. Okay. 60. 981916.968, something like this I'm getting. So it's similar to 9819117 milligal. Yeah, Srinal got T. It's clear. I think you guys have done mistake in the latitude. Okay, can I move to the next question?
Yes,
Sorry.
yes, yes.
Okay. Okay, everyone else clear? Is it beta 1? It is. Okay, I'll move. So the next question is, or similar kind of question is there. What is the value of G corrected for latitude correction during the gravity for a location having coordinates 70 degrees south? Beta 1, beta 2 is given, and gravity at the equator. Okay, 0.86 I have not given. You can consider that also. 0.86 also you can consider, no issue. Okay, and just calculate. Tell me how much you are getting. This will be the last question, I guess. The assignment this time is very easy. I have seen, so it's very easy. Srinath, you were saying something about assignment three's question. Did you get that, or should I do that? Week three's assignment. You were saying something. Um, I don't remember.
Uh, I have calculated and recalculated. They are showing clay to be at a depth of around 1.5 meter, 1.2 meter. I am getting 3 meters.
Okay.
At that depth, we are getting something else.
Srinath, are you getting the similar kind of answer that Mr. Satish is getting? If not, I will do that. It's not a problem. I will do it. Okay, first let me tell me the answer of this. How much you are getting? Then the question might have some issue. Okay, if both of you are getting the same, then I will do it. I will post it in my folder
Oh,
on Google
I
Drive.
have checked number of times that 1.2 or 1.5 which they are telling is
Uh,
never coming. 3 meters, yes, we are getting.
both of you are getting 3 meter. It's possible then. Okay, I'll check. If I am getting 3 meter also, then I will let you know in the next class. Or if you want, I can do now also. I think you guys have done correct only because both of you are having same answer now.
Yes, yes, check number of times.
Okay, then okay, I will do it later. If there is some other answer I am getting, I will post it, or else I will tell you in the next class. You tell me the answer of this first. How much you guys are getting? Maybe Srinath tell A. Anyone else? Similar to the last question that we have seen. Here I have not given east and west so that you guys will not get confused. Gopal, are you getting the answer? Also 10th question I have got 37.4 bar. Okay, okay, both of them, both of question 9 and 10 I will check. I'll let you know by the next week, or I will post it in the folder. Okay, so the answer for this will be A only. Okay, if you do the calculation. So this one was the last question. Yes. So after this, the main advantages and the disadvantages of the gravity service are in my mobile. I can't handle these calculations. Sorry for that. It's fine. Okay. Yeah. You understood like what we are doing and how to do that. If that's
Yes, yes.
then it's fine. Then it's fine. Okay. So what I was saying. So the what are the main advantages of the gravity survey method is okay. Next page I will do. So main advantages or the main point of the gravity survey method is it is the only geophysical method which will provide you the density of the subsurface medium. Density of like not density of the medium everyone is giving, but direct measurement of the like direct measurement without any artificial source. It will give you the density of the medium. So it is one of the main advantages of the gravity survey method. Okay, even if we say like it has limitations because the instrument only will cost you much, and as it is non-destructive and it can be used in urban areas and all, used in urban areas, that's it. Okay, so the main important advantage of the gravity survey is it will give the direct measurement of the density of the medium. Okay, so that's it for today. Any questions, any doubt? The assignment 3 is 9th 10th. I will also see if I'm getting the same. I'll tell you the next day also. Okay, I think
Well presented.
thank you. Any other doubts, any other questions, or any other questions from the previous lectures or today's lecture? Any other questions you can tell me. If not, we'll wrap it up. 34.7 he is getting. Okay, let me write that 34.7 he is getting. Okay, thank you for your patience then. We'll wrap it up here. You guys can leave.